Hello everyone! In this video we will learn how to set up a basic ray tracing study in COMSOL Multiphysics. We are going to simulate ray propagation through a thin lens that you can see over here. In the first scenario, we are going to assume that the object is far away from the lens such that the rays entering the lens are parallel with the optical axis, and as you can see over here, all the rays are being focused. In the second case that you can see over here, we're going to place an object or a light source at the focal point, and as a result you're going to obtain this simulation over here. As expected, the rays are going to propagate through the lens, and after propagating they're going to be parallel with an optical axis. That means that the image is projected far away from the lens or at infinity. We're going to use a thin lens equation to verify this simulation, to compute the focal distance, and to see how well the thin lens equation, or the so-called Lensmaker equation, can predict the behavior of the real physical system. I created a post that accompanies this video. In this post you can learn more about basic ray tracing, about thin lens equation or the Lensmaker's formula. You can read more about what happens when you put an object at a focal point, and then you can read more about under which conditions your image is being projected into the focal point. A link to this post is given in the description below. In order to properly set up the COMSOL study and in order to be able to analyze the results, we need to have at least some basic understanding of geometrical optics and of a thin lens system. Consider a simple lens system, a simple thin lens system. We have an object point whose image is being projected on the other side of the lens. So the ray propagates through air. We assume that the surrounding is air with the index of refraction of approximately 1, and the ray refracts through lens and is being focused at the image point I. We assume that the distance from the front vertex of the lens to the object is SO, and we assume that the distance of the image point from the back vertex of I is actually SI. Now, since the lens is thin, these distances will be approximately equal to distances from the center of the lens. Here, this image is a bit exaggerated. This lens is much thicker than it should be in reality. We assume that the following parameters of the lens are given. NL is the index of refraction of the lens. R1 is the radius of the front sphere, and R2 is the radius of the back sphere. So we are assuming a spherical thin lens. Obviously, the distances SO and SI are related. And the equation that relates these distances is the so-called thin lens equation or Lensmaker equation. Now, the Lensmaker or thin lens equation reads as follows: 1 over SO plus 1 over SI is equal to NL minus 1 multiplying 1 over R1 minus 1 over R2. The thin lens equation is very useful for us because it enables us to estimate the position of the image point if we know the position of the object point. I'm deliberately saying to estimate because in reality, the computed distances, the computed SI, will probably be different from the real distance. Why? Because the thin lens equation is derived under some assumptions. The first assumption is paraxial ray assumption, meaning that the rays emitting from the object form a relatively small angle with respect to the optical axis. Then the assumption is that the lens is thin, and there are a few other assumptions. Maybe these assumptions look a bit restrictive to you. However, my experience and our simulations later will show that thin lens equation is able to relatively accurately predict the position of the image point. Let's see what happens when the object is far away from the lens. That is, when the object position approaches infinity. So, if we put here in this equation, if we say SO is infinity, we'll obtain something like this. The first term will die out. Okay? And then we will obtain that the image position is given as follows. And this specific image position for which that is actually generated by the object that is far away from the lens is called the focal distance. So this will be our focal distance. In this case, all the rays coming from a distant object will be focused into a single point. Even in this case this will happen, but the difference is that the object is far away. So graphically, this means if the object position tends to move away from the lens, what happens with rays? So let's say if the object position is here, the rays look like this. If the object position is here, the rays will look like this. So from this analysis, we can see if the object moves to infinity, the rays coming from the object will become parallel to the optical axis. In infinity, the rays are parallel. And these rays are going to be focused into a single point whose distance can be predicted by the following formula. So from this formula over here, we can compute the focal distance. And the focal distance, f, let's denote it like this, f, will satisfy the following equation. So 1 over f will be equal to NL minus 1 multiplying 1 over R1 minus 1 over R2. On the other hand, let us see under which conditions the image point is projected far away from the lens. So, if the image point is far away from the lens, it means that the distance goes to infinity. So from the Lensmaker equation, we have 1 over SO plus 1 over infinity is equal to NL minus 1, 1 R1, 1 over R1 minus 1 over R2. The second term goes to 0, so we have 1 over SO is equal to NL minus 1, 1 over R1 minus R1 over R2. Now, obviously, this expression is the same as the expression we obtain in the case when the object point is far away from the lens. That is, SO will be equal to the focal distance again. So it's 1 over F is equal to NL minus 1, 1 over R1 minus 1 over R2. What does this means in reality? Okay? We have that if we place an object at the focal point of the lens, its image will be projected far away from the lens. That is, if the rays coming out of the object look like this, the lens will straighten it up and the output rays will be parallel to the optical axis, which means that the image will be projected far away from the back surface of the lens. And this distance is again the focal distance, F. In our COMSOL simulations, we are going to verify these conclusions. So here is the plan. In the first case, we are going to estimate the position of the focal point using the Lensmaker's equation. That is, for a given NL, R1 and R2, for a given lens parameter, we are going to find F. Then, this is the first step. In the second step, we're going to emit rays from the focal point of the lens, and we're going to see what happens on the right hand side of the lens. Will our conclusion be valid? That is, we want to see something like this. If we emit rays from the focal point, we should expect to see the following graph. Then, in the third case, or actually in the second case, or the third point of this video, is to verify that if the object is far away from the lens, that is, if the rays are parallel with an optical axis, we want to verify that these rays will be focused at a specific point, and that this point, F star, will be equal to the point predicted by the Lensmaker equation, or the point we used in our computation. That is the computed point. In this case, or under these circumstances, we are going to verify the accuracy of COMSOL simulation, or on the other hand, we're going to verify how well a thin lens equation can predict what happens in reality. Before we start with COMSOL modeling, we need to compute the focal length. For given lens parameters, R1 of 125, R2 of 100, however, here we choose the sign minus, since the second surface is oriented like this, it's not oriented like this. In this case, if we would have a lens that looks like this, R2 will be positive. However, since R2 is oriented like this and the whole lens is convex, we need to choose a minus sign, and for the refraction index of 1.45 we compute the focal length of 123.46. We will enter this number in COMSOL Multiphysics. So let us start with COMSOL modeling. We click on Model Wizard, 3D, then we click on Geometrical Optics, we click on Study, we click on Ray Tracing, and we click on Done. Now, the first step is to define a lens. Now, we can define the lens manually by extruding, revolving surfaces, etc. However, there is a smarter way and quicker way to define the lens geometry. COMSOL has a predefined library defining standard geometries. So we right click on Geometry, we choose Parts, Part Libraries, and here we click on Ray Optics module, 3D, and we can choose from this list type of mirror or lens that we want to include in our model. In our case, we are going to choose a spherical lens. More precisely, we are going to choose spherical lens 3D. And here is the description. We click on spherical lens 3D, and here you can choose two options. We are going to choose the first option, specify clear aperture diameter, and we click on OK. Okay, we can build the lens. So here is the basic lens object. Of course, we don't want lens to look like this, so we are going to adjust the parameter. We are going to select the following parameters: R1 125, R2 minus 100, center thickness of 10, D0, D1 and D2 are going to be 55, 50 and 50, D1 clear and D2 clear are going to be 45 and 45, and we're going to change the local optical axis. We're going to choose Y optical axis, and we click on Build Select. So here is our lens. The optical axis is in the Y direction. Besides the spherical lens, we will need another geometrical object in our simulations. So we're going to click on Geometry, Parts, Part Libraries, and under the Ray Optics module, 3D, Apertures and Obstructions, we're going to choose Circular Planal Annulus, and we're going to click Add to Geometry. So why do we need a circular planar annulus? Well, we need this object in order to define an image plane. Next, let us adjust the parameters of this object. We're going to choose D0 of 60 millimeters. D1 will be 0. The displacement will be in the Y direction, it will be 100, and rotation angle will be 90. Click on Build Select. Let's see what do we get. We get something that's far away from our lens. Why is that? Because here we need to adjust, we need to specify millimeters. So here is our structure. Finally, we just need to adjust the plane of rotation or the axis of rotation. We're going to choose XW axis, and here it is. This is our structure. This is the lens, this is the image plane, and the rays will be emitted from here. The next step is to define the lens material. So we click on material, we click on add material from library, and we expand this section. Here we can choose built-in materials, and you need to find silica glass. So we're going to choose a silica glass as our material. We'll double click, and here it is. Here it is. Here is the refractive index. This is all we need to have for our simulations. Let us now define geometrical optics properties of our simulation. We click on geometrical optics. We're going to have monochromatic light, right? Here we are not going to analyze reflections, so we're going to choose here maximum number of secondary rays as 0. Then here under the material properties of exterior and unmatched domain, we're not going to change anything since the refractive index of air is approximately 1. Here we can specify that we want to compute intensity, and this is not necessary in our computations, right? But we are going to choose compute intensity, we are going to compute the phase, and here we're going to click on compute optical path length, count reflections, and store ray status data. So the most important thing here is to specify this parameter as 0. If you do not do that, you will see in your simulations rays that will reflect. Next we click on medium properties. You're not going to change the medium properties. However, in this section you can manually specify the refractive index of the lens. However, we are going to use refractive index given in material description, so we are not going to change that. The next section basically specifies material discontinuity. You can specify coding, for example, on your lens or on your mirror, and you can change the parameters here. Release reflected rays, we're going to choose never in our simulations, okay? And here under the section ray properties, you can choose the wavelength. We're going to choose 660 nanometer wavelength. The next step is to specify the boundary conditions. So we're going to assume that the rays that hit the edges of the mirror are not being propagated. We are going to simply erase them from our simulations. So we click on geometrical optics and we click on vol. Now we can select the areas of the mirror. We are going to click over here. Here, oh, this is a mistake. You should be very careful. Just zoom in and click. And the vol condition will be disappear. So the rays that will reach the outer edge of the mirror, or these surfaces, side surfaces, will disappear. Next we define another boundary condition. Again, we click on geometrical optics, we click on vol, and we click on our annulus. And the condition will be freeze. So the rays that reach this surface will not be propagated. This will be our image plane. The next step is to define the point from which the rays are released. We click on geometrical optics and we click on release from grid. And here we can specify the point, we can specify the type of the rays, and we can play with some other parameters. So from the grid type, we're going to click on specified combinations, and here we're going to put focal length distance that has been previously computed, and here we should specify millimeters. So what will happen? We're going to release the ray from this point. Now for the ray direction vector, we're going to choose conical. We're going to choose uniform density, and we're going to choose 100 rays in wave vector space. The cone axis will be directed in the y-axis. Remember that y-axis is our optical axis, and the cone angle will be pi over 24, since we want to have paraxial rays. You can also play here with initial phase and with other parameters. The final step is to define what type of study we want to do. So you click on Study 1, Step 1, Ray Tracing. Here we have two options. We can specify time steps, so we can calculate ray behavior or ray propagation at certain time instance, of course in nanoseconds, right? Or we have another option that we are going to use in this simulation. We're going to specify the maximum path length. So the maximum path length in our case is going to be 1 meter. This is more than enough for rays to reach the image plane. You can also play with some other parameters here, but that's it. This is all we need to do, and we click on compute. Okay, and you click on zoom extent, and here's what you get. Here's the result. Okay, why do you see only one piece? Well, here you can select times, right? You can select the last time, you click on plot, and here it is. Here is our ray propagation. Let us make this graph a little bit more prettier than it is. Click on Ray Trajectories 1, and Color Expression. And here we are going to enter GOP.L. So what we are doing by entering GOP.L? Well, the ray colors are going to correspond to the optical path length. And let's click on plot. Here it is. So the ray colors are optical path lengths. Why this graph is important? Well, this graph is actually the graph from the beginning of our video, and it demonstrates that a thin lens equation, or the Lensmaker equation, is able to accurately predict how the system will behave. Remember that we have computed the focal distance using the length, using basically the thin lens equation, and the theory predicts that if we place an object at the focal point, the rays that are refracted from the lens will be parallel to the optical axis, and this is what happens. Our COMSOL simulations prove that. On the other hand, this is also a verification that COMSOL computations are correct. In our next video, I'm going to demonstrate you how to simulate the second case. And the second case is when basically object is in infinity or far away from the lens. And in the second case, you're going to have that these rays were going to be focused at the focal point, and the simulation will look like this. This will be the release plane, this plane will be the release plane, and this will be, the other part will be the image plane. Thank you very much for your attention.